All right, so have you ever written some R code and it was just mysteriously slow? Or maybe you made one tiny change and boom, all your memory was gone. Well, if that sounds familiar, you are in exactly the right place. We're about to go under the hood and see how R really deals with memory. And trust me, getting this right, it's pretty much the key to writing code that's not just faster, but way more efficient. Okay, let's kick things off with a little puzzle. Imagine we create X, right? It's a vector with a million random numbers, and it takes up about 8 megabytes of memory. Simple enough. Then we make a list called Y, and we stick X in there 3 times. So here's the question for you. How much memory is that list Y really using? I mean, is it 24 megs? A bit more? Just kind of lock that answer in your head for a bit. And hey, let's do one more. Here's our second puzzle. We've got a vector A. Then we make a new thing, B, and just say B equals A. Finally, we go in and change the very first element of B. Now, we all know that A itself isn't going to change, right? But the real question is, when did R make the copy? Was it on line 2, the moment we created B? Or was it on line 3 when we actually changed it? You know, the answers to both of these are, well, they might surprise you. And to find them, we've got to go under the hood. We need to build the right mental model for how R actually thinks. Once you get this, I promise it's a total game changer for how you'll look at R code from now on. All right, so this brings us to what is, honestly, the single most important idea we're going to talk about today. It's this. In R, names are not objects. Seriously, if you can wrap your head around just this one thing, everything else will just click into place. So what's really going on here? Let's break it down. When you type something like X equals 1 through 10, you're not just doing one thing. You're actually doing 2. First, the name X gets created in what's called your environment. Think of it like a directory. But the actual data, the numbers 1 through 10, that gets stored somewhere totally different in your computer's memory. So the name X is really just a label, like a signpost that points to where the real data lives. So if we want to get the lingo just right, we're not really naming an object. What we're doing is creating a binding. That little arrow, left than sign, its whole job is to create a connection, a link, from the name on the left to the value on the right. The value itself doesn't even have a name. It's just sitting there, in memory, completely anonymous. And this right here, this leads to a huge misconception that trips up so many people. We're all taught to think that Y equals X makes a complete copy of the data. But it doesn't, not at all. R is way smarter than that. All it does is create a new name, Y, and it points that new name at the exact same chunk of data in memory that X is already pointing at. Absolutely no data gets copied in that step. And hey, don't just take my word for it. We can actually prove this with code, which is pretty cool. If you use the Lobster package, there's this function called object address that shows you the unique memory address where the data is stored. And look at that. The memory addresses for X and Y are identical. It's proof. They are 2 different names pointing to the very same thing. So, if just assigning a name doesn't make a copy, then when on earth does the copy happen? Well, that brings us to R's secret weapon for efficiency, the copy on modify rule. So here's the main idea. R is lazy, but in a really good, efficient way. It puts off making a copy until the absolute last possible second. A value will only get copied if 2 things are true. 1, it's about to be changed, and 2, there's more than one name pointing to it. Both of those have to be true. Let's see this play out. So remember our Y and X. They're both pointing to the same vector. Now, what happens the moment we try to change the third element of Y? Well, this is when R suddenly wakes up and goes, whoa, hold on a second. Y is about to change, but hey, X is also looking at this data. If I change the original, I'm going to mess up X. And we can literally watch this happen in real time with a function called traceMem. The instant we try to modify Y, R sees that X is still pointing to that original data. So before it does anything else, it first makes a fresh copy of the data at a new memory address. Then it modifies that new copy, and finally it tells Y to point to the new location. And what about X? It's left completely untouched, still pointing to the original unmodified data. Pretty clever, right? Okay, so now we know the big rule, but every rule has exceptions, right? And understanding these exceptions, well, that's the secret to writing some seriously fast R code. So there are basically 2 big exceptions where R just throws the copy on modify rulebook out the window for the sake of speed. First, if an object has only one name pointing to it,
R is smart. It knows it can just modify the data directly. We call that in place, no copy needed. The second exception is a special type of object called an environment, which is always modified in place, always.
Okay, let's look at why this is such a big deal. On the left, we've got a loop, a super common task where we're just subtracting the median from each column of a data frame. On the right, we're doing the exact same thing, but with one tiny change. First, we convert the data frame to a plain old list. You would not believe how much faster the second one is. The difference is just staggering.
So why is a data frame version so painfully slow? It's all about those sneaky, hidden copies. See, modifying a data frame column isn't one of those special exceptions. So on every single pass through that loop, R is copying the entire data frame, maybe even more than once. If you're working with a big data set, this is an absolute performance killer.
But when you modify a list, you tap into some super optimized internal code. R recognizes it can just tweak each element of the list in place without having to copy the entire thing over and over. And the result? 0 copies. The code just flies. Seriously, this one little trick can save you so much time. All right, we've covered the core ideas. Names are pointers, and R copies on modify. Now, let's get to the fun part. Let's use what we've learned to finally solve those puzzles from the beginning. Okay, first up, let's go back to that memory puzzle. Remember this? We had our 8 megabyte vector x, and then we made a list y that held x 3 times. So what was the final answer? How much memory does it all take up? And the answer is, drumroll please, just 8 megabytes. Well, okay, to be super precise, it's about 80 times bytes more than the original vector x. Pretty wild, right? Were you surprised? And here's why that works. That list, y, it doesn't actually contain 3 copies of the data. No way. It just contains 3 pointers, 3 little signposts. And all 3 of those signposts are pointing to the exact same single 8 megabyte vector in memory. The list itself is incredibly tiny because it's just storing a few addresses. This is R being super, super efficient. All right, and what about that second puzzle? We have A, we set B equal to A, and then we change B. So on which line did the copy actually happen? The copy happens on line 3, right at the moment of modification. Let's think it through. On line 2, when we say B equals A, R just creates a new pointer. No copy. But on line 3, just before it changes the value, the copy on modify rule kicks in. R looks and says, hey, A and B are both pointing here, and B is about to change, so it makes that protective copy for B right then and there. So there you have it. Names are just pointers, and R is smart. It only copies data when it absolutely has to. It seems like a simple mental model, but it is so powerful. It explains so much about why some code is slow and other code is fast, and how R uses memory. So the real question to leave you with is this. Now that you know how R thinks, how is that going to change the way you write your code? Something to think about. Thanks so much for joining me.